All right, section 2.5, the precise definition of a limit. Anybody that's going to become a math major, you're going to do a lot with this. And different calculus professors spend different amounts of time in this section. I've seen some that will spend an entire 2-hour lecture and give a bunch of homework on this and so forth. I've seen other professors that completely skip this section. The guy whose course I copied, those extra videos that you don't have to watch, he doesn't even do this section. He skips it. So I'm going to go kind of in the middle here. I'm going to talk about it for like 5 minutes. And then maybe at some point I'll do like an extra credit discussion on it or something. But I don't think we're going to have any homework. So this is the actual mathematical definition of a limit. That whole, well, as x gets closer to a, y gets closer to L, we're going to formalize that here. And the formal definition says that the limit as x goes to a of f of x does in fact equal L if for every epsilon greater than 0, there exists a delta greater than 0, such that if the distance between x and a is less than delta, then the distance between y and L was less than epsilon. So it's like this game that we're playing. So I'm making a claim. I think I know what the limit is. I think the limit as we approach a is some number L. So here's the game we have to play. You pick some number epsilon, some small number, some distance away from L that you want me to stay inside, some window. See this little window right here? You get to pick epsilon, and then it's my job, because I'm the one making the claim, to find some delta down here. And what's supposed to happen is any of the x values that live in this window, a distance delta or less away from a, their y value will end up being close to L. How close? Within epsilon. So you pick an epsilon, then I get to say, okay, based on that epsilon, I'm going to choose this delta. And then as long as we use any of these x's, all of those y values will live inside that window you chose. And then you go, okay, I'm going to pick a smaller epsilon. So you pick a smaller window here. And then I go, okay, then I'm going to pick a smaller delta. So here would be this delta based on that epsilon, that distance. All of these x values, when I plug them in the function, spit out y values that live in that window you chose. And then you go, well, all right, I got you now. I'm going to pick a smaller epsilon. And then I go, okay, that's all right. I found a smaller delta. If I can always do that, no matter how small your epsilon is, if I can always find the delta so that the y values are close to epsilon, as long as x is close to delta, then I win the game. So in other words, no matter how close you want me to be to L, I can find x's close enough to a that will spit out y values that close to L. That's the game. And if I win that game, I've proven that L is in fact the limit. Okay, so here's an actual proof. Again, in some sections of this class that are going on right now, they might be spending an entire week on this, and the students might have to actually write up proofs like this. I'm just going to show you a proof. Okay. So this proof is already kind of worked out. I'm going to go through it backwards so you can see how everything was solved, how it was figured out. So we're trying to prove that this limit as x approaches 1 of this function does in fact equal 3. So the game is supposed to be for every epsilon, there's some delta that depends on epsilon, so that as long as the distance between x and 1 is less than delta. Then the y values, the difference between the y value and the limit will be less than epsilon. So let's start there. That's where we want to end up. So just like combining like terms there, we get this. Now, really what they did here, I'm going to skip up a couple of steps. They factored a 2 out. So that's really 2 times absolute value of x minus 1 is less than epsilon. Or in other words, I'm going to write that. If I divide both sides by 2, this line right here really says that says the distance between x and 1 is less than epsilon over 2. So we just kind of worked backwards from where we want to end up. Well, then that means as long as I choose delta to be this number or smaller, if delta, that's an ugly delta. If delta equals epsilon over 2, that would imply that if my distance between x and 1 is less than delta, then the distance between x and 1 would be less than epsilon over 2. And then working backwards, multiply both sides by 2, distribute the 2, and split this up. So this was working backwards to try to find out, you give me epsilon, what do I want delta to be? Okay, now that we got that, that's all just scratch work. Here's what the actual proof would look like. You always start these with, let epsilon be greater than 0. That's some arbitrary number. Then I already worked this out ahead of time. I know I want my delta to be epsilon over 2. Then if this is happening, then this thing that I'm looking at, the distance between the function and L, the limit, equals that. Pull out the 2, pull the 2 out of the absolute value. Wait a minute, I know that thing's less than delta right there, so this line must be less than twice delta. But I got to choose delta. I chose delta to be epsilon over 2, so this thing here must be less than epsilon, right there, that less than. That's what a formal proof would look like. So when does this kind of proof fail? When do limits not exist? Well, maybe if we had maybe a function that looks like this. So maybe this is, I don't know, 3 and 5. So if you claimed, maybe you claim the limit as x approaches 1 of f of x is 3. Where would this precise definition fail? Well, I could choose maybe epsilon equals 1. So that means there should be some region here between 2 and 4. There should be some region around here so that all the y values live between 2 and 4. That's my epsilon there, that distance. But it won't work. No matter what delta you choose, you could choose any little tiny distance delta you want right here. These y values right here are all going to be up here. They're not going to live inside that window. So this will not work because that limit doesn't exist. Okay, like I said, we're not going to do much with this. Maybe I'll make an extra credit discussion and have you try one later, but I'm not going to put it on the test. I just wanted you to at least see the precise definition.